Okay, let's now plug in some numbers with this quantity, right? So we said that given any alpha, any parameter alpha, by setting L equals t minus root of gamma by alpha and r equals t plus root of gamma by alpha is a valid alpha confidence interval, right? So because gamma is known. Okay, and let's plug in two different values for this because these are values that we've already seen. If I set alpha equals 0.04, then C will be equal to 5 because this is equal to root of 1 by 0.04 happens to be 5. And in this case, the confidence interval becomes T minus 5 root gamma and R is equal to T plus 5 root gamma. Okay. So I have some value for gamma and I have this estimator T, which is some function of x1 through xn, and T minus 5 root gamma, T plus 5 root gamma. So if you recall, our idea was to start with T and say that I'll pick T minus delta T plus delta, and delta I'm saying is like 5 root gamma if I want a confidence of 96%. Okay, likewise, if I want a confidence of like 99%, then I'll have to choose alpha to be 0.01, which corresponds to C equals 10. So let's now see how this works in the case of a Bernoulli. Okay, so this again we saw last week, but I'd like to recap it. Okay, so Bernoulli distribution, you have a single parameter which is P. Okay, and probability of 1 is P, probability of 0 is 1 minus P. And now you have x1, x2 up to xn that are drawn from the Bernoulli distribution, and our goal is to find an estimator for P and get good confidence intervals. Right. So last week, what we saw, which is kind of nice about this, about estimating the Bernoulli, is that the natural estimator, which is T, which is the empirical average. Let's know that this is the empirical average of the exercise. Okay, so this empirical average estimator using n samples has a mean squared error that is roughly 1 by n, right? So this is less than or equal to 1 by n. Okay, in fact, we saw that it's exactly equal to p times 1 minus p divided by n. Okay, so firstly, this was an unbiased estimator. That's one thing we saw. Another thing is that its mean squared error is p times 1 minus p by n, which is always, actually we saw that this is less than or equal to 1 by 4n. Okay, so t has a mean squared error that drops with n. Now, suppose I plug in what I just said before. Okay, so suppose I want a 96% confidence interval. Then I've got to plug in alpha equals 0.04, which corresponds to C equals 5. Okay. Now, that just means that L, so mean squared error was 1 by n, okay, which means that if I really want, I could have written 1 by 4n over here, which gives us slightly better confidence intervals. Okay. Now, right, so let's plug in C equals 5. You get L being this and R being this. Okay, and this is for 96% confidence. Okay, what is the length of the confidence interval over here? The length of the confidence interval is the difference between L and R. Okay, that's equal to 10 by root n in this case. Okay, at least if we did this calculation, if we plugged in this value, you would have got 5 by root n, but doesn't matter. Let's stick with MSE being 1 by n. Okay, so the length of this confidence interval is like 10 by root n. Okay. Now, the main observation I'd like to make is that as n, which is the number of samples, grows, the interval shrinks. Okay, the interval length shrinks. Okay, and this is assuming that you care about the same level of confidence, right? So I am fixing this 96% level of confidence, and I am increasing n. Okay, and my confidence interval is now reducing, right? So if I pick n equals 100, okay, now the confidence interval had length which is like 10 by root of 100, which is 1. No, that interval of 1 is pretty useless, right? Because interval of length 1 is useless because I always knew that p lies between 0 and 1. Okay, so at least using this bound I know that this is pretty useless. But if I were to choose n equal to 10,000, then root n becomes 100, and now this length of the interval L minus R is only 0.1. Okay, now I'm getting somewhere, right? So if n equals 10,000, I'm getting L minus R being equal to 0.1, which is quite good, right? So I'm able to isolate P to a pretty reasonable accuracy of 0.1 with high confidence, right? With 96% confidence. Okay, so this is one very simple application of how Chebyshev and this whole mean squared error based confidence intervals, I mean what they give us. Okay. So one issue with this whole process, you already seen it over here, right? So which is that in the first example when I spoke of n equals 100, right? So this way of estimation or this way of getting confidence intervals is not particularly tight in the sense that the bounds seem to have a lot of room for improvement, right? Because I was using 100 samples and I wanted 96% confidence. So 100 samples, if you think about it, is a fair amount. Okay. Now, and I'm only able to get a confidence interval whose length was like 1, and 1 is like this trivial guarantee that you have, right? And this actually becomes worse. Okay, so this becomes worse if you want higher confidence, right? So the reason this was happening is because you wanted a confidence of 96%, and that's why you had this 5 by root n and so on. Okay. Now, if I were to plug in, for example, 99.99, right? So that's like saying alpha equals 1 by 10,000, and that's like saying C equals 100. Okay, so I'm plugging in alpha equals this value, and that corresponds to C being 100. Then my interval will have will look like t minus 100 root gamma and t plus 100. Yeah, I know what root gamma is by root n, and t plus 100. Okay. And this is pretty bad, right? So if I want this quantity to be even less than 1, right? So this term to be less than 1, then I would like to have n being more than root n more than 100 or n more than 10 to the 4. Okay, so you need like a lot of samples to be able to ensure that you have like this kind of confidence. Okay, and if you want in a smaller interval, let's say I want an interval of length 0.1, okay, then I would need n to be more than 10 power 6. Okay. By the way, this is the sort of computation that you will see in your last homework, and this is the kind of thing that you should start getting comfortable with. Okay, so that's the weakness with this bound, which is that somehow the calculations become pretty weak when your desired confidence level becomes high. Okay. Now the question is, can you obtain shorter interval lengths with the same kind of confidence, potentially using a more direct kind of a computation? Okay. And this is what is possible if by using, there's a short answer to this, which is that in many cases you can actually obtain this using what is called the central limit theorem. Okay, so what is the central limit theorem? We'll see that in a little while. But the summary of what the central limit theorem implies in this case is that if you want, like if you ask what is the right value of C, so here C was turning out to be root of 1 by alpha, right? And the central limit theorem, in short, implies that C being something like 2 log of 1 by alpha, square root of 2 log 1 by alpha, is actually the right answer. Okay, or it's in some sense that's also a valid bound. Okay, so instead of using C equals root of 1 by alpha, if we use the, and this was obtained by Chebyshev, if I use the central limit theorem, you end up with a root of 2 log 1 by alpha, and this can be significantly better than root of 1 by alpha when alpha is very small. Okay, so if I plug in alpha being 0.001, here I was getting C equals 100. If I plug in this value, you can evaluate this, you end up with a value of like 4.3, okay, which is way less than 100. Right, so your interval length goes from like 200 by root n to something like 8.6 by root n, okay, which is a much smaller interval. It's like 20 factor more or something. Okay, and in fact, if alpha gets smaller, then this becomes even better than this one. Okay. So that's the power of the central limit theorem. One way of viewing it is as saying that it gives much tighter intervals, and these are usually actually the best possible intervals that you can get. Okay. And that than what simple computations like Chebyshev give you. Okay. But the caveat, this big caveat, which is that this philosophy or using central limit theorem is not always possible. Okay. It's possible only if you have n being large enough and so on. Okay. But it does happen to be true in the case of, but it is applicable in the case of Bernoulli. Okay, so we'll next see what the central limit theorem is. We saw this already last week, but I'd like to quickly recap this and why this sort of a computation shows up.